Good morning, students. Welcome to Measure Integration live lectures. In this lecture, we will discuss about general Lebesgue integral of a measurable function. Okay. So far what we have seen is, if you just recall quickly, we have defined Lebesgue integral for first is simple function, right? So if phi is a simple function, if we write this as summation ai chi of ai, then what is integration of phi? Of course, everywhere over e. Huh? How integration of phi is defined? Quickly. Huh? If phi is like this, how integration is defined?
Summation
Summation.
ai integral of
It is chi of ai, so it is measure of ai, right?
yes sir.
You are not studying. You will study only for exam or what? Then second one, we have defined integration for f bounded function. Of course, every time we are taking measurable functions. Then for a bounded measurable function, how integration of f over e is defined in terms of simple functions we have defined. How we have defined? Can somebody tell? If f is a bounded measurable function, then how integration of f is defined? Using simple functions. Every day at least one or two times we recall that definition. This is infimum of integration of this psi, if you want to write this as psi, okay, where psi is greater than or equal to f, psi is a simple function.
Simple.
And this is also same as supremum of integration of phi less than or equal to f,
Yes.
and phi is simple. Huh? Whatever you know it, you should tell. Otherwise, what is the point? I keep on saying and you will listening. Huh? Then next, what is our next step? That if f is a non-negative measurable function, okay, then integration of f over e we have defined as supremum of, in terms of bounded functions we have defined. How we have defined is supremum of integration of h, okay, h is less than or equal to f, and of course it is bigger than or equal to 0. So where h is bounded measurable function with finite support. Is this clear? Bounded and finite support. And we have seen several properties and also two results. Okay, convergence, related to convergence results, bounded convergence. So some theorems what we have seen is bounded convergence theorem. Okay, then we have also seen Fatu's lemma, and we also proved monotone convergence theorem, along with properties of integral, okay, of a measurable function, no matter whether it is simple, bounded, or non-negative. Right? Now we will define for general Lebesgue measure, the general Lebesgue integral. Okay, that means, so we will define now general Lebesgue integral or integration, you can call it. That means we will take f any function, not necessarily f greater than or equal to 0, or not necessarily it is bounded and so on. So you take any f, a measurable function, then can we define? So if f is any measurable function, measurable function defined on e, then how we can define integration of f over e? Okay, is the question. So obviously this we will define using in terms of non-negative functions, f greater than or equal to 0, right? So for that we define what is meant by positive part and negative part. Then we will see how we can define integration of f using that. Okay, so given any f, so given any function f, so positive part of f is defined as f plus of x. Okay, you simply denote by f plus. So this f plus of x, name itself suggests, is same as f of x if your f of x is greater than or equal to 0. And whenever f of x is less than 0, that means negative, we will simply define this as 0. Is definition clear? F plus of x, huh? This f plus and
Yes,
f
sir.
both are same when it is greater than or equal to 0, and f plus, whenever f is negative, we are taking f plus as 0 only. Is this clear? Yes or no?
Yes, sir.
Yes, sir.
So therefore this you can
Yes,
also
sir.
define this as maximum of f of x comma 0. Is this clear? Because if f of x is less than 0, then what is maximum of these two is 0. Yes or no? If f of x is greater than
Yes,
or
sir.
equal to 0, then maximum is nothing but f of x. Okay.
Yes.
We can also define this in terms of characteristic function. This is same as f times characteristic function of the set f of x is greater than or equal to 0. Is this clear? Because whenever f of x is greater than or equal to 0, then this chi of that value is 1 and it is f times 1, which is f of x. Whenever f of x is less than 0, then characteristic function value of this characteristic function is 0, so this is 0. Any problem? So any of these three ways you can define. Similarly, what is f minus negative part of? Similarly, negative part of f is denoted by f minus of x. How it is defined? It is minus of f of x if f of x is less than or equal to 0. So just like mod x, how we define mod x is x if x greater than or equal to 0 and minus x if x less than or equal to 0, right? And 0 whenever f of x is greater than 0. Are you following? So your f
Yes,
minus
sir.
is nothing but minus of f of x whenever f of x is less than or equal to 0, and 0 whenever f of x is greater than 0. So this is same as, of course you can again write maximum of minus f of x comma 0, or this also you can write as minus of minimum of f of x comma 0. Okay, or in terms of characteristic function, how you can write this? You can write as minus f times characteristic function of f of x less than or equal to 0, because at these values this characteristic function is 1, so you get minus f. Yes or no? Any problem?
No.
Then we can observe that, so you can call it as a remark about this positive and negative part, that f plus and f minus both are greater than or equal to 0. They are non-negative functions. Why? Because this f plus is f of x, or 0 greater than or equal to this, right? Yes or no? F plus is greater than or equal to 0 because f of x is also greater than or equal to 0, right? Any problem? Similarly, if f of x is less than or equal to 0, you are taking minus of that. So therefore, minus of f of x is greater than or equal to 0. So your f minus is also greater than or equal to 0. Is that clear? F plus and f minus both functions are non-negative functions. Yes or no?
Yes.
Yes, sir.
Then second
Sir.
one, if you observe this f plus minus of f minus, by definition, if you write in terms of these characteristic functions, f plus is nothing but f times characteristic function of f of x greater than or equal to 0, or if you just write 1 greater than also, no problem. Okay, then minus, what is your f minus? Is minus f times characteristic function of f of x less than or equal to 0. Is this clear? This is same as minus of minus, this will become plus. Okay, so this is f times characteristic function of f of x greater than 0, right, plus f times characteristic function of f of x less than or equal to 0. But this is whatever you have characteristic function of two sets, okay, they are disjoint sets. Yes or no? F of x greater than 0, this is a disjoint set. All x says that f of x greater than 0 and all x says that f of x less than or equal to 0, right? So therefore this is same as what you will get, f times characteristic function of that entire where it is defined. Is this clear? Any problem?
Yes, sir.
That entire domain, but
Yes,
this
sir.
value is 1. So what you get here is 1, f. Is that clear?
Yes.
So f is defined on E. See what is meaning of this one? This is nothing but whatever we are writing here. This is actually all x, this f of x less than or equal to 0. This is actually set notation that x says that f of x is less than or equal to 0. Is this clear? So here x says that f of x greater than 0 is coming and x says that f of x less than or equal to 0. So all x is coming. That means it is chi of E. Chi of E is 1. Okay, because every element is coming from that domain, so it is 1. So f is nothing but, so therefore what we have noticed is that f can be written as f plus minus f minus. Similarly, you can check that absolute value mod f is nothing but f plus f minus. Okay, so I'll leave it this as exercise. Verify f plus f minus is same as mod f. How you will do? Hint, because mod f of x, okay, if mod f of x, you do it by doing into two cases. Case 1 is that f of x is greater than or equal to 0, then what is mod f of x? If f of x is greater than or equal to 0, what is the value of mod f of x? Is same as f of x. And second case, if f of x is less than 0. So in both cases, show that this left hand side is same as right hand side. Are you following? Yes or no?
Yes, yes, sir.
Okay. If you have any difficulty, you can ask whenever you are not finding. Next class, you can ask. Okay. So these are all. Then you can see that if f plus and f minus are, because f is written as f plus minus f minus and mod f is f plus f minus, right? So this integration of f we can define in terms of f plus and f minus. Okay, so definition that integral of f, that is general integration. That means your f is any measurable function. If it is integrable, then we can define, right? So the definition we can define as a measurable function f is said to be integrable. A measurable function f is said to be integrable, is said to be integrable, or E, or on E, on a measurable set E, if this f plus and f minus are integrable. F plus and f minus are integrable. That means their integration is finite. And integral of f and integral of f is, or E is defined as, in this case, integration of f over E is, because we know integration of f plus, because f is non-negative, so this makes sense and it is finite. Similarly, integration of f minus, and you take their difference. Is this clear? No? Is definition of integral of any measurable function is nothing but we are defining in terms of its positive part and negative part, right? Yes or no? So if one of these
Yes.
f plus and f minus, they are not integrable, then f is not integrable. Okay. So if both are integrable, then f is integrable, and integration of f over E, the value is defined as the difference of this integration, right? Okay. Now we can see some simple properties for this integration of f, where f is any measurable function, right? So for whatever we have seen, the same you can prove it. So if you want, you'd write as proposition that let f and g be integrable functions over a set E, where E is measurable set. Okay. Then what are all arithmetic so far we have seen? Huh? This integration of c times f over E is same as c times integration of f over E, where c is any real number, right? And what is second one? About this is scalar times. The second one is about linear. That means integration of f plus g over E is integration of f over E plus integration of g over E. Then third one, monotonicity. That means f is less than or equal to g almost everywhere. Then integration of f over E is less than or equal to integration of g over E, right? So this properties, and not only this, about disjoint also. If A and B are disjoint, okay, two disjoint measurable sets, then integration of f over A union B is same as integration of f over A plus integration of f over B. So these four properties we have seen every time or not? Every time means what? In all these cases, if f is non-negative, we are shown. If f is bounded, for that also we have seen those properties. Even for simple functions, we have seen such properties, right? Is that clear? Hmm?
Yes, sir.
So we can quickly prove. Only thing is, every time the definition of that integration of f is different. So proof is little bit different. But every time the results are hold. Okay. First one is obvious. You can do it. Integration of c times f. So if you want to find integration of c times f over E, so I will explain one. This by definition how it is defined. The positive part of CF minus the negative part of CF. Is this clear? So clearly if C is equal to 0, there is nothing to prove, right? So assume C not equal to 0. So if, say, suppose C is greater than 0, then can you tell me what is C times F plus by definition? No, this is same as C times f of x. If you write here f, if C times f of x is greater than or equal to 0, I am rewriting the definition of C, positive part of C times f, right? And 0 if
Yes, sir.
C times f of x is less than 0. Is this clear?
0.
This, can you write C times, that means positive part of CF, can you write in terms of positive part of f? Because we know we want to write somehow the right hand side. It should be integration of f plus minus integration of f minus, right? So this is same as C, I can bring it outside or not? F of x, huh? And C is greater than 0. So C I can send here. So f of x is greater than or equal to 0 and f of x is less than 0. Is this clear? Any problem? So this is same as C times f plus of x. So therefore, positive part of CF is same as C times positive part of f. Is that clear? No? Similarly, you can easily check that this negative part of C times f is same as C times negative part of x, because here minus will be there, right? Minus C times, so C will only just take out C, and C you send it here, you will get f minus. Okay, so therefore this integration of C times f over E is same as integration of E CF plus minus integration of CF minus over E, but CF plus is same as, this is same as integration of E C times F plus, okay, minus integration of C times F minus. But now this F plus is non-negative, yes or no? So for non-negative, this result is already true for all whatever these 4 points. They are already true for non-negative measurable functions. So this scalar I can bring outside, yes or no? This scalar I can
Yes, sir.
bring outside. Similarly, this scalar I can bring outside, right? But what you have here is nothing but integration of f over p. Okay, is this clear? Now, if suppose c is less than 0, then what you will get? Huh? Then can quickly tell me what is cf plus is of x is c times f of x if c times f of x is greater than or equal to 0, and 0 if c times f of x is less than 0, right? But can I take it this is same way? Is it same way? That means what is this f of x will become? If I send c to this side, what is this inequality will become? Huh? Because your c is less than 0, so if you take this c this side, what you will get? F of x is less than or equal to 0, yes or no? Huh?
Yes,
Because we are multiplying by a negative value, this inequality will change and this will become f of x greater than 0. Are you following?
0.
Yes or no?
Yes,
So this is same as c. So I can bring this c outside, it is not a problem. C into f of x and this one, right? But if f of x is less than or equal to 0, if we have minus c here, right, then this will become f minus. Are you following? So we don't want just f of x, we want minus f of x, right? So I will multiply this here minus. Any problem? Huh? So therefore this is same as minus c times what you have here is nothing but f minus of x. Yes or no? Have you understood this?
Yes,
sir.
sir.
Huh?
Sir, how would the minus come?
Because here what we have here is f of x is less than or equal to 0. So if f of x is less than or equal to 0, how our negative part is defined? F of x is less than or equal to 0, it should be minus of f of x. Are you following? Okay.
Yes,
So
sir.
here f of x is less than or equal to 0 and c you can take outside, but we don't want f of x here, we want minus f of x. So this c you can write as minus of minus c. Is this clear? See, if I take
Yes, sir.
minus c inside, it is minus of minus plus c times f of x only. Are you following? Huh?
Yes, sir.
But now whatever this flower
Yes, sir.
bracket, this function is defined, it is precisely f minus. For that purpose, we have written here minus, and outside also we have written minus, right?
Yes.
Okay. So therefore, similarly, what can you say about c minus of x? Huh? It is same as minus c will be here and f of x, right? Where c times f of x. How this is defined? We can quickly write. This is same as minus c times f of x. If c times f of x is less than or equal to 0 and c times f of x greater than 0, this value is 0, right? But again c is less than 0. So if c is less than 0, if you take this c this side, f of x is greater than or equal to 0 and f of x is less than 0, right? Now because it is f of x is greater than or equal to 0, we want only f of x here, right? So I can take out minus c outside. This is same as minus c times f plus of x. Is that clear? Any problem? Hmm?
Yes, sir.
Have you understood this? Yes or no?
Yes,
Only
sir.
this relation,
Yes, sir.
whatever we have here, we are trying to defining for in terms of f plus and f minus. That's all. Therefore, integration of cf over e is integration of cf plus, but cf plus is same as minus c times f minus c times f minus, okay, and minus of what is integration of cf minus is minus of c f plus, okay. So if you take outside scalar, then it is f minus minus of minus plus is this. Is this clear? Again, if you take c common, then it is integration of f plus minus integration of f minus, right? Integration of f plus minus integration of f minus, which is same as c times integration of f over e. Okay. So only here to just come to know what is positive part of scalar times a function. That is the only thing we have done here. Okay. Quickly, what is second one? Integration of f plus g. We want to show that integration of f plus g over e is integration of f plus integration of g, right? So for this, first we show that if f1 and f2 are non-negative measurable or integrable, you call it integrable, non-negative integrable functions such that f is equal to f1 minus f2, not necessarily f plus minus f minus. Then also we'll show that integration of f over e is equal to integration of f1 over e minus integration of f2 over e. Okay. So first, what we are proving, if at all your given integrable function is difference of two non-negative integrable functions, not only f plus and f minus, then also integration of f over e, we can write it as, we can show that it is same as integration of f1 minus integration of f2. Okay, so this is our claim. How we can prove it? Given that f is equal to f1 minus f2, where f1 and f2 are greater than or equal to 0. But f you can write as f plus minus f minus. Is this clear? Is same as f1 minus f2, right? This is nothing but you can bring it f plus f2 this side and f1 plus f minus this side. Okay, if you take, they are all non-negative, all are non-negative functions. Therefore, integration of f plus f2 over e, right? This is same as integration of f1 over e plus integration of f minus over e. Yes or no? Because monotonicity is this linear property is true for non-negative integrable functions. Now, because their integrations are finite, you can bring it one side, that means integration of e over f plus minus integration of f minus over e is same as integration of f1 minus integration of f2. But left hand side, whatever you have here is nothing but integration of f over e is equal to integration of f1 over e minus integration of f over e2. Sorry, f2 over e. Is this clear? So what we have proved is that even if f is f1 minus f2, where f and f2 are non-negative integrable functions, then integration of f is integration of f1 minus integration of f2, right? So we use this. Therefore this f plus g, how we can write this f plus g? We can write as f plus minus f minus. That means this is the value of f. Is this clear? Right? Or you write now f plus g is nothing but similarly g plus minus g minus. Okay?
G.
Any problem? Now, can you write this one? If you rewrite this, it is same as f plus g plus minus f minus minus g minus. Is this clear? Here you will get plus, right? If I take minus common, then it is f minus plus g minus. Are you following? So this is like, this is
Yes.
just like your f1 and this is just like your f2. Is this clear? Right? And we know
Yes.
because f plus and g plus, f minus g minus, they are all integrable. So their sum is also integrable, right? This implies just now by claim whatever we have proved, integration of f plus g over e is same as what? Integration of e, this f plus g plus minus integration of f minus plus g minus. Is this clear? Yes or no? Since by claim.
Yes, sir.
But now you can apply linear property for f plus and g plus because they are non-negative. So this is same as integration of f plus over e plus integration of g plus over e minus integration of f minus over e minus integration of g minus over e. Right? This is same as if you combine this, you will get integration of f over e plus if you combine these two, you will get integration of g over e. So that proves linear property. Is this clear? Now the third one is not at all difficult. If f is less than or equal to g almost everywhere, then you have g minus f is greater than or equal to 0 almost everywhere, right? Therefore, by using integration for non-negative, what you get is g minus f over e is greater than or equal to 0. But using linear property, this is same as integration of g minus this is greater than or equal to 0, right? But that is same as saying that integration of g over f is greater than or equal to integration of f over e, right? Similarly, fourth one is also obvious. The integration of f over a union b we want to find is same as integration of f into chi of a union b, right? But this is same as integration of f into chi of a plus integration of f into chi of b because a and b are disjoint, right? Okay, but again applying linear property, what you will get is integration of f over f times chi of a plus integration of f times chi of b. But again this is same as integration of f over a plus integration of f over b. Okay, so there is nothing new. It is same as how we have proved for non-negative case. Okay, these are the basic results of the integration of any general measurable function, right? Now what we will prove is the interesting result called Lebesgue convergence theorem or Lebesgue dominated convergence theorem. Lebesgue convergence theorem, or sometimes it is also called as Lebesgue dominated convergence theorem, LDCT. Okay, so you will see why this dominated term is coming here. So far how many convergence theorems we have discussed? I have written here. They are all similar to convergence, related to some convergence, right? Here, bounded convergence theorem, Fatu's lemma, monotone convergence theorem. Okay, now we'll see for this any general sequence of measurable functions. Okay, any problem?
No, sir.
No, sir.
Okay, so what this Lebesgue dominated convergence theorem says that if you have a sequence of measurable functions fn, so let me write this statement, then we'll discuss. So if you write, say, like, let g be integrable over a measurable set e over e, and fn be a sequence of measurable functions, okay, such that this mod fn of x is less than or equal to g. That means mod fn is less than or equal to g for all n. That's why we calling it as dominating. So if at all there exists an integrable function which dominates every measurable function given fn, then that limits and integral can be interchanged. Okay, now so if fn of x converges to f of x almost everywhere on e, then integration of f over e is limit of integration of fn over e. Okay, see Lebesgue convergence theorem or Lebesgue dominated convergence theorem, the result, output, okay, is same. Integration of f over e is same as limit of integration of fn over e. But there condition is different. There we are taking fn's non-negative and increasing function, right? Whereas here you are dropping the condition that they are non-negative. It can be any sequence of measurable functions, but they should be a measurable integrable function g such that mod fn is less than or equal to g. Is this clear? Huh? Yes or no?
Yes, sir.
See, if you see from this one, this entire statement is same as what? Is same as monotone convergence theorem. Okay? Or it is same as even that bounded convergence theorem also. But only difference is what? That assumptions. Here, whatever you are having here, that is different for every statement. Right? Clear? Hmm? And proof
Yes.
is not at all difficult. First of all, whenever we want to talk about integration of f over e, we want to make sure that f is integrable. Then only we can define this, right? That is follows from, since mod fn is less than or equal to g for every n, this implies limit of mod fn is also less than or equal to g, right? But you can take limit inside, so therefore this is same as mod f is less than or equal to g. Now as g is integrable, as g is integrable, we get that f is also integrable, because integration of g is finite, is integrable. Okay, right? Now we'll show that integration of f over e is limit of this. What we use is simply we'll use this Fatou's lemma to prove this, right? As mod fn is less than or equal to g for all n implies your fn, your g is what you will get here. Mod fn is less than or equal to g is same as fn is less than or equal to g and greater than or equal to minus g. Is this clear? This is true for all n. Okay. If you remember what is Fatou's lemma? Fatou's lemma is for any sequence of non-negative measurable functions. So you have here Fatou's lemma. You can check here. So what it says is that if you have fn is a sequence of non-negative measurable functions, so you should require only condition that they should be non-negative. And whenever fn x converges to f of x, then integration of f is less than or equal to lower limit, right? So how we can apply Fatou's lemma here to this general Lebesgue integral? Just a second. So here, because we do it in two, let me load, it is loading a little bit. So now this one time we'll consider this fn is less than or equal to g. If fn is less than or equal to g and minus g is less than or equal to fn, right? So this implies we get that g minus fn is greater than or equal to 0 for all n, and not only that, this fn plus g or g plus fn is also greater than or equal to 0 for all n, right? Yes or no? So this is a sequence g minus f1, g minus f2, g minus f3 and so on. So by Fatou's lemma, what we get? Integration of g minus fn over e is less than or equal to lower limit. That means lim of integration of, this is g minus f. Why? Because your fn's are converging to f. So therefore g minus fn is converging to g minus f, right? So this is nothing but g minus fn, okay, over e. Is this clear? What is the reason? Since your fn converges to f almost everywhere, so g minus fn converges to g minus f almost everywhere. Similarly, g plus fn also converges to g plus f almost everywhere, right? But this one is same as, if you take lim inf inside, what you will get? Because it is first one is independent of that n, so it is same as integration of g e plus, okay, lim inf of, okay, what you have here is minus of integration of fn. Is this clear? Minus will come outside integration, but lim inf of minus of something is same as what? Is same as, when you take minus outside, this will become minus of lim sup of integration of fn. Is this clear? Any problem? Now left hand side, by monotone linear property, what you get is this. Is this clear? Here you have less than, right? Integration of g over e minus integration of f over e is less than or equal to this. But because g is integrable, so therefore that integration is finite value. So we can cancel both sides, and if you cancel minus, then this inequality, what it will become? Integration of f over e is greater than or equal to lim sup of integration of fn over e. Is this step clear, everyone? Yes or no? How lim inf is changed to lim sup? Because lim inf of some minus of a is there set. Yes or no? Are you there?
Yes.
Okay. Similarly,
Yes, sir.
you can apply now for fn plus g greater than or equal to 0. Similarly, by applying Pareto's lemma for this fn plus g greater than or equal to 0, what we get is integration of this f plus g, okay, over e is less than or equal to lower limit of integration of fn plus g over e. Okay, now if you take this, this is same as integration of f over e plus integration of g over e is less than or equal to this lim inf of integration of fn, right? Lim inf of integration of fn over e, and this is same as integration of g over e. So g over e integration will get cancelled. So integration of f over e is less than or equal to lim inf of integration of fn over e, right? So therefore you take these two, what you will get? If you take this as 1 and this as 2, by 1 and 2 you see that you will get they are equal. Why? From 1 and 2, from integration of f over e is less than or equal to, by second it is same as less than or equal to lim inf of integration of fn over e, okay, but we know lim inf is always less than or equal to lim sup, limit superior, right? Then by 1, lim sup is less than or equal to integration of f over e, right? But now you see that extreme ends, they are same, right? So therefore all should be equal. That shows that integration of f over e is equal to lim inf of integration of fn over e, which is same as lim sup of integration of fn over e. So whenever lim sup and lim inf equal to something, okay, which is finite value, then this is nothing but the limit, right? Limit of integration of fn over. Is this clear? So that proves this Lebesgue convergence theorem, or you can also call it, this is Lebesgue dominated convergence theorem. Is this clear? Any doubt? Any doubt?
No.
Okay. Now this g also we can replace by sequence of measurable integrable functions gn's, okay, or sequence of measurable functions gn's, such that fn is less than or equal to gn. Then also we get this. So we'll just state this statement. Proof follows same way. So let me state generalized Lebesgue convergence theorem. That means we can drop that condition that G should be integrable. In place of taking G is integrable, we'll replace that by the sequence of measurable functions Gn. Okay. So this statement is, and proof is similar. Let Gn be a sequence of integrable functions such that Gn converges to uh, an integrable function G, okay, almost everywhere. Even you can take almost everywhere, it is not a problem. Now let Fn be a sequence of measurable functions, okay, such that mod Fn is less than or equal to Gn, and for every n, okay, and Fn, okay, converges to f of x almost everywhere, okay. See, what is the difference between this statement and previous statement? That all functions Fn's, the one single function G is dominating every function. Mod Fn is less than or equal to G for every n, whereas here it is little weaker. That means it is you don't need to f1 should be less than or equal to G1, that's all. F2 should be less than or equal to G2, F3 should be less than or equal to G3, and so on. Is this clear? So we are not demanding that all mod Fn should be less than or equal to some particular G, right? Okay, so that condition is here, we have made it weaker, so that's why it is more general. So if Gns, okay, that means our integration of G over E, if this is same as limit of integration of Gn over E, then our integration of F over E is limit of integration of Fn over E, okay. So whenever this is true, then integration of F over E, this is also right. What is proof where these changes will come? Because each Gns are integrable for this entire thing, proof is same wherever G is there. Here what you will get? In place of G minus Fn, what you will get? Gn minus Fn, because Fn is less than or equal to Gn. So you will get Gn minus Fn. Is that clear? So you apply Fatou's lemma, you get
Yes.
Gn minus, because here hint I will write here, you can complete that. So I'll give hint, so you write as exercise, only hint I will give, that your mod Fn is less than or equal to Gn implies you have this Fn is less than or equal to Gn and also greater than or equal to minus Gn. That means you have Gn minus Fn is greater than or equal to 0, and Gn plus Fn is greater than or equal to 0, right? Now also that your Gn's converges to G, right, and Fn converges to F. This implies Gn minus Fn converges to G minus F, right? So therefore you have a non-negative measurable functions Gn minus Fn converging to G minus F, right? Yes or no? This implies by
Yes, sir.
Fatou's lemma what you will get is integration of G minus F over E, right? Is what you will get is less than or equal to lower limit of integration of Gn, right, minus Fn. Is this clear? Yes or no?
Yes, sir.
But integration of G over E is same as limit of integration of Gn, those two will get cancelled, right? That's why we require this condition. So I ask everyone to complete this proof similar to like this one, okay? Yes or no? It is very simple. I have written everything here, that much only you have to follow now. Take this is limit, this is limit, and complete it. If you have difficulty, you ask, okay? I'll explain. If you don't ask, then you are the loser, okay? So this is about how we have defined Lebesgue integral of any measurable function, and we have seen their properties and Lebesgue dominated convergence theorem, okay? So we'll stop here.